Assalamu alaikum and a very good day. This will be the final video lecture of this dynamics course, and today we are going to talk about the angular impulse and momentum. Let's look at the lesson outcomes of this class. At the end of this lesson, you should be able to understand the difference between moment of force and angular momentum. You should be able to understand the principle of angular impulse and momentum. You should be able to understand the conservation of angular momentum. And finally, we're going to solve a few problems related to angular impulse and momentum. Let's look at the moment of force. What is a moment of force? You have learned about this in statics. Moment of force is basically when you have a force acting in this direction, for example, and we take point O as the reference point. So when we are going to calculate the moment about point O, then what we do is we multiply the force F here with the distance D. That is the distance between the reference point O and the force F. So that is what we call the moment of force. So moment of force MO is the force F multiplied with the distance of F from O. In this case, we call this as D, the distance. So in scalar quantity, MO is equals to F times D. In vector, we can write this as M is equal to the force cross product R, which is the position vector from O to the particle. Now let's look at what is the angular momentum. This is an almost similar term, whereas the angular momentum is now, if previously we have a force here, now this is replaced with momentum, and as what we have learned before, momentum is equal to mass times the velocity. So mass is a scalar quantity, velocity is a vector quantity. So when you multiply a momentum with the distance D about the reference point O, then what you have is the angular momentum. So if in the previous lesson, linear momentum is written using a symbol L, the angular momentum now uses the symbol H. And since this is rotation about point O, then we're gonna write HO is equal to the momentum mv multiplied with the distance D. That is the distance from point O to the particle. Okay, so this is the difference between the moment of force F times D with the angular momentum. Now force becomes momentum m times v multiplied with the distance D. So basically the angular momentum is almost, you can also say that the angular momentum is the moment of the momentum. Okay. Now, in the previous lesson, we have learned about the principle of impulse and momentum, and specifically we discussed about the principle of linear impulse and momentum. And this is what we have. Principle of linear impulse and momentum is mv1, that is the momentum, initial momentum, plus the total impulse is equal to the final momentum. mv2 is the final momentum. Now the principle of angular impulse and momentum, now you're gonna put another parameter here, which is the distance D, then this will become the angular momentum. And this part here, to convert this force initially into momentum, we have to multiply with d as well. So force times d is the moment, and when you integrate the moment about time dt, you will get the angular impulse equals to mv times d. This is another angular momentum, which is the final angular momentum, and d here is the distance from the particle to the reference point O. And previously we write the principle of linear impulse and momentum as L, initial linear momentum, plus the total impulse equals the final linear momentum. So for the principle of angular impulse and momentum, we have HO1, that is the initial angular momentum about point O, plus the integration of MO dt, which you will get the angular impulse about point O, and equal to HO2, that is the angular momentum about point O, the final angular momentum about point O. So this is the principle of angular impulse and momentum. This is basically the extension of what you have learned previously, that is the principle of linear impulse and momentum. Now, if we are talking about two-dimensional problems, now you will have three equations that you can use to solve the problem based on the situation of the problem, and you decide which equation to use. So you have the principle of linear impulse and momentum in x-axis. You have the principle of linear impulse and momentum in y-axis, and finally we have the principle of angular impulse and momentum with a rotation about point O. When in any cases the impulse, the angular impulse is equals to 0, then what we have, like what we had in the previous lesson also, we're going to have the conservation of angular momentum, which states that the initial angular momentum about point O is equal to the final angular momentum about point O. In the case of there are more than one particles, then we're going to have a system of particles. So the summation of initial angular momentum about point O is equal to the summation of the final angular momentum about point O. So this is the conservation of angular momentum. So basically what we have covered today is the principle of principle of angular impulse and momentum, and also the conservation of angular momentum. To understand this better, let's look at a few problems. Example problem 1. Initially, 5 kg block is moving with a constant speed of 2 meters per second around circular path. So you can imagine the motion of this box here is going to be a circular path at center point O. So by looking at this problem, we know that it is better to solve this using the principle of angular impulse and momentum, because this involves rotational motion. The particle here, the green particle, the green block, is moving in a circular path surrounding the center point O, and therefore we should use the principle of angular impulse and momentum. So the mass of the block is 5 kg. It has initial speed of 2 meters per second. It has a constant tangential force of 5 Newton applied to it. So we need to determine the speed of the block when t equals to 3 seconds. This is obviously should be solved using the principle of angular impulse and momentum. And From our previous slide, we know that HO, the angular momentum, is the mass multiplied with the velocity multiplied with the distance from the particle to the center, to the reference point O. In this case, it is equal to 1.5 meter. So we have the equation HO1, initial angular momentum about O, plus the total impulse from 0 to 3 seconds equals to the final angular momentum about point O. So here we have mvd. M is 5 kg, v is 2 meter per second, initial speed is given in the problem, and d is 1.5. As for the moment, we have a force here, 5 Newton. To convert this force into a moment of force, you have to multiply with the distance 1.5. Therefore, here 5 times 1.5. And since we integrate over time to make it impulse, we multiply with the time 3 seconds here. So this becomes the angular impulse equals to mvd. v2 is unknown. This is the parameter that we want to calculate. So what we have is v2 equals to 5 meter per second. Let's look at example number 2. 5 kg block, the same block, is now moving around point O as well, but then the force applied is in this direction, and it changes over time. It is no longer a constant force. It's 10 times t, where t is in seconds. So as the time increases, the force applied also increases. If the block starts from rest, now this is slightly different from what we have in problem 1. Now the block starts from not moving. So we need to determine the speed of the block when t equals to 4 seconds. Okay, this is again a rotation problem, so we need to use the principle of angular impulse and momentum. And we know HO is mvd, but then the moment here is something that we need to pay attention to. The force is applied in this direction, but what we are calculating is basically in the tangential direction here. So we need to resolve this force into this axis here, and what we have is 10t multiplied with 4 over 5. We have a small triangle here, 3, 4 and 5. So this side here is basically the cosine of this angle, so it is equal to 4 over 5. So this force is the one that we should put in the calculation here, and not this resultant force of 10t. So HO1 is 5 times 0. The velocity is 0 because it starts from rest, so the whole thing becomes 0. This is the integration from 0 to 4 because t is 4 seconds. 10t times 4 over 5, and to convert it into to convert the force into moment, we have to multiply it with d, that is 1.5. And this is equal to 5 v2 times 1.5. Again, this is mvd, the angular momentum. So for this part, the integration part, what we have is 1.2 is 4 over 5 multiplied with 1.5, you'll get 1.2. And from this, you get 10t square over 2. So you have 10, t is 4 square, divided by 2, you have 96. So substitute in this equation up here, you'll get the velocity v2 is equal to 12.8 meter per second. The final example for today's lesson is this example problem 3. At the instant r equals to 1.5 meter, this is r 1.5 meter, 5 kg disc is given a speed of v equals to 5 meter per second. So this disk here is moving at 5 meter per second in this direction, in this tangential direction, perpendicular to the elastic cord. The cord is elastic, okay? Therefore, it behaves similar to a spring. So you can notice that the coefficient of the spring coefficient is given here, 200 Newton per meter. Determine the speed of the disk and the rate of shortening. So due to the circular movement, the cord will be wrapped around this point A, and therefore it becomes shorter and shorter. The cord becomes shorter. So determine the speed of the disk and the rate of shortening of the elastic cord at the instant r equals to 1.2. So because the cord is getting shorter and shorter, so it starts from r equals to 1.5, then the length of the cord slowly or gradually reduce. So what we want to find is what is the speed of the disk when r equals 1.2, and what is the rate of shortening during this moment. The disk slides on smooth surface, therefore we should neglect the friction. The cord has unstretched length of 0.5. This is an important information here when we calculate the elastic potential energy of the cord. Okay, let's draw when r equals to 1.2. So the cord has moved here. The disk has now moved here with r now is equal to 1.2. And because we know that this cord is shortening, therefore the velocity of the disk is no longer in the tangential direction, but it is pointing inside, closer to the center of rotation, which is point A. This should be how V2 is pointed, okay? And because of this direction, we can then draw the components of V2, and if you imagine the motion, it becomes closer and closer to the center, and this can be represented by a cylindrical coordinate, and therefore that is why this coordinate is given is written as V2 transverse. This is a transverse coordinate, and this is the radial coordinate pointing towards the center. Okay, so initially we need to determine the speed of the disk. So which one is the speed of the disk? It is the V2. V2 is the resultant velocity, is the speed of the disk at this moment. And what is the rate of shortening? It is represented by the radial component of the velocity, okay? Because the radial component is moving towards the center of rotation, and this represents the rate of shortening, how fast the cord is being shortened due to the motion. Okay, that is the rate of shortening. So first, to calculate the speed V2, we need to go back to chapter 3, and we need to apply the conservation of energy. The conservation of energy states that the initial kinetic energy plus the initial potential energy is equal to the final kinetic energy plus final potential energy. And in this case, there is no change of height happening, therefore there is no gravitational potential energy. But since the cord is elastic, therefore we know that there is an elastic potential energy. So T1 is half mv1 square, V1 is therefore half ks1 square, and T2 half mv2 square, V2 is half ks2 square. T1 is 1/2 times 5 kg times 5 square. This is the initial velocity, 5. plus half ks1 square 1 over 2 times 200. This is the spring constant. S1 is the initial length, which is 1.5 length of the cord, minus the unstretched length, which is 0.5. So this, the whole thing is squared. On the right hand side, you have 1 over 2 times 5 the mass, and v2 square, this is an unknown, we want to find out, plus 1 over 2 times 200 times, now 1.2 is the length of the cord at this instant, minus the unstretched length of 0.5, and then the whole thing is squared. And finally, what you will get is v2 is equal to 6.738 meter per second. Okay, this is the velocity or the speed of the disk when r equals to 1.2 meter. So now the second thing that we have to calculate is the rate of shortening. And remember, the rate of shortening is represented by the radial component of the velocity. Therefore, we need to find what is this. But we cannot find this straight away. But what we can do is we can find this first, the transverse component, because it is in the same axis as the initial velocity of the disk. So in this case, we can use now the conservation of angular momentum, which states that initial angular momentum at this point is equal to the final angular momentum at this point. So HO we have defined before, that is equal to mv times d. So in this case, m times v1 theta, which is actually this 5 meter per second, is equal to m multiplied with r1. R1 is 1.5, is equal to mv2 theta times r2. So we substitute the values in. So m is 5, v1 theta is 5, r1 is 1.5. On the right hand side, m is 5, v2 theta is unknown, and r2 is 1.2. So from here, you will get the transverse component of v2 is equal to 6.25 meter per second. And what's left is then to calculate v2r, that is the radial component. Since we have this equation v2, this should be v2 squared. This is a typing mistake here. v2 squared is equal to v2 theta squared plus v2r squared, and therefore finally we will get v2r, the radial component, or in other words, the rate of shortening of the elastic cord is equal to 2.518 meter per second. Okay, therefore, in summary, today we have learned about the principle of angular impulse and momentum. We have learned about the conservation of angular momentum, and finally we have solved a few problems related to angular impulse and momentum. And with this, we have finally finished the dynamics course, or to be specific, the course of particle dynamics. Thank you.